Thank you, Jonathan, and thank you to the organizers for having me speak on some topics that are dear to me. I found have geometry and applications coming from minimal geometry, so it's going to be a mini course in 3 parts. And as Thomas explained in his course just before, I will say something about the Monty-Mumford conjecture. First, I'm going to start out with historical facts. I'm not going to give a complete history, some brief overview, and what is known on the conjecture. It's brief, so I can already say that. And then in the second part, which is going to be the main part of the main course, I'm going to give a proof sketch of the conjecture of Monty-Mumford for abelian varieties defined for algebraic Q, and using the theorem of Pilo-Wilke that was described at the end of the last talk. So the proof will be in the spirit of this paper of Pilo that was also presented before. And so in fact, the sketch I'm going to give will apply the Pilo-Wilke theorem twice. Once as in the Pilo paper, and once to look at the problem of functional transcendence, and that is also in the spirit of Plato works of Pilo and the upfront compact case, compact normalized. Okay, and if there's enough time, I'll conclude third lecture with the outlook on unlikely intersections beyond unlikely conjecture. Okay. So the first section would be Monty-Mumford. So the setup, the classical setup is as follows, and I'm going to usually, well, not always, but I'll try to keep the notation. C will be a curve over the field of complex numbers. And what do I mean by curve? This is going to mainly mean a smooth projective curve that is irreducible, smooth projective algebraic curve defined over the field of complex numbers. Later on, we're going to change the base field a bit, but this is what we keep in mind at the moment. Now, of course, you know, any curve has a genus. So we'll be genus curve. It's non-zero, non-negative integer. And well, of course, for genus 0, because we're over the complex fields, projective, reducible, and smooth. So there's only one curve here. So C will be isomorphic to P1. And a lot of these people are looking at a sphere here. And we're not going to talk about P1 anymore after this point. So everything that's going to happen is going to happen in genus at least 1. So maybe let's just say single out genus 1, because this will play a particular role here. Well, what is a genus 1 curve? Topologically speaking, looks like a real torus of dimension 2. And what we typically do is we fix a point. And by this, I mean a complex point of the curve. And once I've singled out a point on the curve, I get what I get an elliptic curve, because then I can pair together as an elliptic curve. Right, and sorry, P dot will be the 0 point of an algebraic group law, and uniformize this thing picture. P dot will be here, and it will be unit elements, and so here's a holomorphic group holomorphism. This kernel is a rank 2 subgroup. Of the complex numbers. So the quotient you can think of the curve as the quotient C modulo of this rank 2 subgroup, and E naught is the unit element. So topologically, or at least in the somehow in the real analytic sense, our curve is as a real analytic group, it's isomorphic to R modulo Z squared. So we're forgetting here in this picture, we forget the complex structure. It's kind of a point of view that will be useful later on. So it's just a real torus from the real analytic point of view. So we know a lot about the group structure here, and the Monty-Montfort conjecture, as we'll see, concerns points of finite order on projective algebraic groups, and well, the points of finite order in this group are just those that come from rational substance. And the important case for us will be genus at least 2. And now, topologically speaking, we're looking at this surface with a certain number of holes. It's very nice. 2 holes. Of course, there's no group structure involved here. This is visible here. But what one can do is one can embed the curve into its Jacobian. We still fix a base point. And then we can map any point to the class of degree 0 divisors up to linear equivalence. And well, you can thereby get an embedding of the curve, which find out. Look at this. Get embedding of the curve into a Jacobian, and the distinguished point gets mapped to 0, and this here is G-dimensional, principally polarized containing curves. So in a sense, it's kind of generalizes the genus 1 case, so the non-projective projective algebraic group, and there's also a uniformizing map. So from the complex point of view, this is a complex torus carrying a polarization. It's holomorphic group holomorphism, and the kernel is again something discrete. And C to the G, and this now has rank 2G. So the curve now lives inside some larger. This is, from the real point of view, it is isomorphic as a topological group. R mod Z the future. So guys, that's kind of the basic setup. And now, what does the conjecture of Monty-Montfort say? The conjecture says in these terms, well, this is a theorem. Not sure if there's actually a paper where Monty-Montfort said this conjecture, but Glenn attributes it to these two. And well, it says that genus is at least 2. Then now considering the curve as already being contained inside Jacobian after choosing space point. And the conjecture is that if I intersect the curve with a set of torsion points on the abelian variety, so this is torsion subgroup. Then this is going to be a finite set. Well, there's certainly a point in here because I mapped P naught to 0, so that'll be in origin, but apart from this one, there's only 5. Now I'm really considering everything will be the complex numbers. So the torsion group here is isomorphic as groups to Q mod Z root 2G. So it's currently an infinite group to start out with, but when I intersect it with the curve, somehow I'm only hitting 5 many points inside this point. Okay, so that's the conjecture and the history to the conjecture. Well, maybe when we trace back to the 1960s, And this is in a paper published by Serge Lang, where he publishes three proofs by three independent proofs by Ihara and Tate, not of this conjecture, but of an analog conjecture where the curve is replaced by some one-dimensional algebraic variety, and the ambient group is no longer the Jacobian, but the multiplicative. So a curve here in this sense means not a projective, of course, but a fine curve. So there's an analog statement for affine curves here, where the torsion points in this group are just given by tuples of roots of unity. And there's a condition on the curve here that corresponds to having a genus at least 2. Of course, we can't speak of the genus here because we're not in the projective case, but there's a condition here that mimics this condition, and they obtain the correct fine case results. So this is kind of a precursor to the conjecture of Money-Mumford, which is something about general curves or known varieties. Then yes, they prove finiteness for so the condition is that this curve here is not allowed to be to translate into algebraic subgroup by a point of finite order, sorry, and then make sure that the curve intersects points of finite order in the finite. Yeah, so there are three different proofs in this paper, which was authored by Lang, but he attributes the proofs to RSR. Okay, so maybe I should also say in this context for GN to the N, there's also a large body of work going into higher dimension and not just define curves, but define subvarieties, leading to higher dimensional variance by eventually by Laurent and the independent work of Adam Sarnak and earlier work of Mann and many others. So I'm not going to talk too much about the affine situation. So in the complex, the Italian situation, we have later work of Bogamola from 1980, and he gets finiteness not for the full torsion group, but for a certain subgroup. For all points of the order is a power of, say, of 2 or of any fixed area. Actual number. Instead of looking at all torsion, looks at the torsion points. So it's like the order is a power of a fixed number that gets finiteness in this context. Also, a bit more general dimension. Here, and then finally, okay, the conjecture itself was improved by Renault in 1983. Full conjecture.
Maybe just avoid the very corner.
Okay.
Behind the podium, the bottom right, and stand up.
Okay. I'll try to do this. Is that okay? If I do it over here. So yeah, what did I say? Renault. This was a full conjecture. And in the same year, but in a different paper, even in higher dimension. And I'll say a few words about that in a moment. So the conjecture is proved, and it's been proved for almost 40 years now.
Higher dimension, you mean instead of a curve? That's the higher dimension.
I'm going to talk about that just in a moment, but yeah, instead of a curve, but somehow in an abelian variety already fixed. I'm going to come to that just in a moment. And just to point out that after Renault, there were a lot of new proofs. sometimes also lead to new insights. For example, bounds on the number of points in this intersection, and so on, that we can call effective or using different methods. So let me just break down a few names here. Midrasha we have a model theoretic or point of view of the whole thing. Then we have Pink Rustler. Okay, their account would be more in the language of algebraic geometry, classical. Then, of course, the work of Lasagna, which is the content of this course. And, not putting this in alphabetical order. Mark Hendry, who replaced the abelian varieties by semi-abelian varieties. Gave some results there for Patsy Olmo. Proof that was inspired by work towards the Andreev conjecture. So this is going to be content of the talk. It's going to be lasagna. And the question came, what happens in higher dimension? So what does that even mean here? So we kind of changed the point of view. I mean, we could start out with any nice enough variety and look at algebraics, but we can might as well just start out with an abelian variety. We'll look at kind of subvarieties or abelian varieties as. So we fix A as the abelian variety. Still over the field of complex numbers at the moment. And I might as well just look at any subvariety. So it's reducible. Also the same field. And I can ask when is the intersection of X with version of A is finite. The higher dimensional version. What about X cap being towards? So let me just give you a few examples that kind of stake out what's possible in this higher dimensional setting. Of course, if X happens to be a curve and if A happens to be its Jacobian, then Mannheim gives a finiteness result. The genus of the curve is at least 2. But what happens if X itself is, well, it's the genus 1. Well, genus 0 cannot happen inside of the abelian variety, but genus 1 can happen. And what happens, that kind of corresponds to what happens if, for example, X itself happens to be an abelian subvariety. Let's call it B. Well, I already said something about at the very beginning. Well, any abelian variety is a complex torus, and as such, from a group theoretic point of view, as a topological group that looks like this, the torsion group looks like this. And this holds also for any abelian subvariety of A. So this will be isomorphic as a topological group, R mod C, the 2 times the dimension of B. And the torsion so this is dense in the Euclidean topology, and of course, in particular, in the risky topology. Extensively, both topologies that would be usable in this context. So we have a lot of torsion size. X cap towards is dense. X, if X happens to be a distributed shape, right? It corresponds to the genus 1 case. Right, and so what happens if the same thing holds if I translate X by point of final point. I also get to choose dense and clear dense subset. All right. So that's the first example I wanted to show you. So if X happens to have a nice group structure itself, then we'll have torsion points all over the place. Second example is C. Let's start out with a curve. Where we already know what 21 says in dimension 1, and E is going to be over here. And X is, in this example, is just E cross curve contained in A, and A is E cross Jacobian of the curve. So I'm assuming that the curve is already contained in the Jacobian the usual way. So this is a surface. Now it's X is a surface, there's dimension 2. And what is the intersection of X with a torus? So if I assume I know money Mumford for the curve, then this will be contained in it's equal to E towards cross curve intersected with Jacobian. And if I assume that money Mumford is true, this will be at least finite. But this E torus will always be infinite. Right. This is infinite. So in this example, we see that okay, the curve, the surface hits the torsion in infinite such. This is infinite. So this is finite non-empty. But it's not dense. It's certainly not dense in the Euclidean sense, because this is a finite set. So the closure of this here in whatever topology you like, Euclidean or Zariski, this will be E cross finite. So it's not going to be Zariski dense inside X. So we don't expect finiteness in higher dimensions, but we certainly get non-Zariski denseness in this second example. And in this first example, we get Zariski denseness of the torsion. But this happens to have the explanation that, well, the X essentially comes to the algebraic subgroup. All right. And so these are the only obstructions to, so this is actually the only obstruction here, having non-Zariski denseness of the torsion. So the conjecture is, in fact, the theorem of Reynolds in the second paper, which I alluded to as the higher dimensional generalization, is as follows. The complex fields type above, purely the complex result, but it has proofs. Then X cap A torus is a risk dense. X, if and only if X happens to be of this nature here. X is torsion plus value subline. And this is what sometimes we call torsion cosine. And in the language of unlikely intersections, this is what we call a special subvariety of the abelian variety A. It's kind of a similar language that one uses in the context of Shimura varieties, or our more general notions. So there's the concept of special subvarieties that have some arithmetic meaning. Here, torsion plus value subvariety, and these are the exceptional subsets here that contain a Zariski dense set of torsion points. And so if you replace all the words here, you Belling variety by Shimura variety. Here this by special, this by CM point, the torsion, and you get the one rework. That's kind of like the template to get all these conjectures.
I'm seeing the big intersection in the empty.
Okay, that's just the way I set things up. If I take this, if the curve happens to lie, doesn't have to have non-empty intersection with the torsion, but the way I set it up is a curve. The fixed point gets mapped to 0, so you have that point. But you will have to expect that this is non-empty in general. You could have a point, but only finally, so this is potentially. Okay. All right, so so that's kind of the goal here is to prove this. This is the goal here to prove this theorem. The higher dimensional version. So let's start out. So the section of chapter 2. Proof of Reynolds theorem, maybe. By using the approach by Pila Zanier, and then somehow I'll give it overview of the necessary Axel Lindemann Weierstrass theorem that we need to prove this theorem. So the setup is kind of as in Reynolds theorem. I'm going to not talk about curves and Jacobians anymore because, as you can see, this theorem here implies the original Monty-Montfort conjecture of curves inside the Jacobians, because this cannot happen here in genus at least 2. Okay, so the setup is, I should say, we're going to be working over 2 bar. The setup is, well, the Abelian variety.
So you're changing the setting, right? Rather than working with the complex numbers.
Right. I'm going to prove a special case of this theorem where the Abelian varieties of the or maybe over a number.
And the ideas of the proof are very different from the original.
So the original proof is different from the one by Pila Zanier. And so you can go from Q bar to C by specialization points. So there's a way to reduce the complex case to the Q bar case, which I'm not going to talk about.
A method belonging to logic.
I think you can also formulate it algebraic geometrically in the sense that if you have an Abelian variety over the field of complex numbers and you have it over a finally generated extension of Q, and then you look at it as a family of Abelian varieties and kind of specialized fibers. That's kind of one way that one can go from Q bar and then extend it to the field of complex numbers. It's not always so easy. So in the context of unlike the intersections, the specialization argument is not always so straightforward, but for Monty-Montfort, we have a lot of knowledge on torsion of the Abelian varieties. So I would always assume everything is algebraic closure of Q inside C. So we're going to move back and forth between the algebraic and the complex world. So everything happens inside C. Everything is defined over a number of Q. That's kind of the setup. And well,
You have implicitly have a degree, all of that.
yeah. So implicitly, yeah. So this is exactly what's going to happen. So implicitly, an Abelian variety carries an ample line bundle, so we can already embed it into some projective space. So I want to actually, there are two points of view. So there's the algebraic point of view. So we have, we could just fix an embedding of the abelian variety into some large projective space. And well, everything is defined over K. So this is Pn over K. The embedding is over K. And inside, I'll identify A with its image. And inside Pn, A is just a zero set of some system of polynomials. Homogeneous polynomials in the polynomial ring X naught X. So that's kind of the algebraic point of view. And well, there's also the analytic point of view. Which I already spoke about at the beginning. It's kind of the way these two play together is what makes things interesting. So A is not only a variety, but it's also a complex torus. So there's a holomorphic universal covering map. I should say G is a dimension, right? It's a general notation. So there's a universal covering. So A is also considered as complex points, it's holomorphic, it's rejected, homomorphism. So at least in the complex analytic category, A is C to the G. So we can also consider this a tangent space of A modulo some rank to G. Plus. But okay, I've already said that this is kind of this is being considered as a subvariety of P to the N. So that means, in the sense that we have certain functions in C to the G that take values that will give this. I'll give this a name here. The uniformizing map. Let's identify the points. Then the target will be some from the projective space. And these functions here, they are holomorphic on C to the G. They're almost invariant by this lattice. So there's a factor of automorphy going on. But the theta i's are holomorphic. So yeah, it's the target is somehow projective n space. So there's you can write down this kind of this embedding using classical theta functions, and then there are no corollaries.
They don't have to be defined as polymorphic functions to define louder functions to A and define.
No, not that. Okay, so yeah, so it's not going to be periodic under the lattice. But it's going to be like with a factor of automorphy periodic. So you don't get bounded functions because if you add a lattice point, you're going to get like a factor of fun. That's the same for all.
Is the lattice point, I can think of them as defined over K or
No, the lattice points are in fact generally highly transcendental. Well, there are special cases where they can happen to be algebraic, but the periods are usually transcendental. So this is kind of the transcendental point of view. Whereas this is the algebraic point of view, and it's kind of how these two play together. That's kind of fun. So these are, you can think of these as classical theta functions, and so there's a factor of automorphy going on. So if I add a period or a lattice point, then I'm almost invariant. But there's so you're a factor, but you get the same point in projective space. All right, so let me say this lattice here, this is sometimes also called the period lattice. This is a rank 2G. So we can fix a basis. Lattice, period, lattice basis. And this is what we'll practice later on in the proof. Because the abelian variety is fixed, we can just fix this once and for all. The families of abelian variety care here, but this is lattice basis. And once you fix the period lattice basis, this will induce an isomorphism of C to the G with R to the 2G. You think of R to the 2G as C to the G with the complex structure coming from the fact that, well, this period lattice lies in C to the G. They're not only Z linear independent, but R linear independent. Lattice. R vector spaces. So what we're going to sometimes do is we're going to think of this uniformizing map as being precomposed with this isomorphism coming from choice of lattice basis, and then target is okay. And so this whole thing here. Right? Yeah, I might as well just call it the uniformizing map. So the kernel here is now, the thing is set up in such a way that the kernel here of the full thing is just Z to the 2G. Those are, we're just kind of chosen the basis in such a way that the kernel now is C to the 2G. And the torsion points are exactly the images of the rational points. Okay, so that's going to be useful. These are going to be the rational points that are going to be counted if you are looking for the company. And maybe some example that's some for elliptic curves, we have the classical Weierstrass functions. That's all the differential equation. So the elliptic curve is presented as y squared equals 4x cubed, where it's g2x, where it's g3. That's the non-singular, and then you get Weierstrass p function, you get a lattice, and this p function here will parameterize the curves here. In fact, we do have a pole because somehow the line coordinates and vector coordinates the pole that 0.
As I said, I told you does not depend on the abelian variety. It's always equivalent modulo equivalent.
Well, it does, because it's some of the subgroup of points of finite order of the abelian variety. But as a group, well, as a subgroup, as an abstract group, it's always the same. And even as a subgroup of somehow consider A as a topological group, it always has the same structure. It's kind of the complex structure that's kind of that changes here. The complex structure is somehow encoded in a non-trivial way in this embedding in PPF. But it's kind of the point of this is maybe a different point of view. You see the complex structure also.
And in PPN, the coordinate will be constant.
Not necessarily.
They might.
Yeah, they might be, but for the torsion points, they will be all algebraic.
For those points are already out.
So these points,
You can think of the condition of being torsion imposes that, I mean, you can write it out as a set of algebraic.
that's exactly right. Yeah, and that's what we're going to do just very briefly in a moment. In fact, this is going to be important. Well, it's going to be important that these points are algebraic. I set up the whole thing to be defined over an algebraic extent or a number field so that we can use a Galois Q bar over Q or Q bar over K to get some information later on. Okay, so this is kind of this is the basic setup. These 2 points of view and how they merge will play a role in the proof. And as the next step would be to kind of enter the world of minimal geometry. See, I can erase this. Could be now part 2 of chapter 2. Constructing a definable set. In the end, we want to use the theorem of Pyrrholophy, so we have to be in some a definable subset of R to the n in some minimal structure. And I've almost already set up how things are going to work. So we already have, so the setup is the same. We already have our period lattice spaces between the Abelian variety as presented as a complex torus. We have this uniformizing map, which is holomorphic, and then we fix the period lattice spaces, and then we can identify C to the G with R to the 2G. And we have these theta functions. I'm also considering them as on R to the 2G, coming from this lattice construction here. And they're certainly real analytic because, well, on C to the G, we had something polymorphic. But they're in a sense periodic, not entirely periodic, but almost periodic. And this is actually a problem for minimal geometry, which doesn't allow any periodic behavior because, for example, think of the sine function, which is periodic. The zeros of the sine function can never be a definable set because a discrete infinite set or a countable infinite set can never be definable as infinitely connected components. So this, it's given as itself, can never be definable in any minimal structure. But remember that this map here has kernel C to 2G. So we don't really care about the whole function. We only care what happens on the fundamental domain. So we only care about the restriction of the theta functions here to, if we've been a bit over pedantic, but the half open cube here, 0, 1, 2G, right? Because if I restrict the 0, 1, 2G, I still get a surjective map, right? So this uniformizing map restricted to 0, 1, 2G. Well, these are definable both. First, okay, this is a no minimal. First, let me say something about the compact restriction. So this is now going to be definable in a no minimal structure called structure generated by restrictive analytic functions. And this is precisely the structure generated by restriction of real analytic functions to this hypercube, compact hypercube in this case. So this is definable in Rn. That the fact that this structure here is O minimal is a non-trivial theorem related to works of Gabriello, and we'll hear about it in Thomas's talk. So this is definable, and okay, now I can remove these endpoints again because it's restricted to something semi-algebraic. So what we do is we look at well, the whole thing restricted to this box here. And well, we can still get something surjective, which is good enough for us because we still get all the points on A, and we can get all torsion points by just restricting this here to the rational points in this interval. Okay. But now, okay, what does body number tell us? It tells us something about subvarieties of X. X of A. This would be a subvariety. And X, well, everything is defined. Everything is already contained in some larger projective space by the initial setup. So X itself will be a subvariety of projective space, and some P to the n. And this is a zero set of a certain finite collection of polynomials. Modulus polynomials. And what I'm interested about in now is considering the pre-image. X, well, not everything is restricted to this somehow fundamental. So this restriction here kind of tells me I'm safe to work in no-minimal structure, and this is just the same thing as the points in R or 0, 1 to the 2G, such that for all I, Fi, and then the theta functions here vanish. Right. So I already said that if you restrict to 0, 1 to 2G even half open, you get a definable function. And what I'm doing here is just composing with polynomials, and polynomials, they're certainly definable. You have to be a bit careful because K is a subfield of C. So in this setting, you kind of identify C with R to the 2G, sorry, with R squared in the usual sense. So this will be definable here as a function in X, and the zero set will be the definable set in R.
So you know, so what is the left hand side?
This is by default, yeah. This is the pre-image here.
So it's after you do the entire thing,
Yeah, the whole set, the whole subdividing X.
but you just leave the entire X.
And this whole thing
X
is-
inside of it. It's not it.
Yeah, X is inside A, so subdivided. If you take X, you can also take A itself, and then you'll just recover 0, 1 to 2G. So this is now sum defined. It's just a pre-image of X under uniformizing map. So if you just take the pre-image without restricting, you'll get many copies of the pre-image, just to translate it all around. And what this happens, restriction we're just singling out one. And that happens to be defined as same. And this, I'll call this curly X.
It's fine, but in this part, reality,
Yeah, in Rn. You're right. So inside A, we have something like this. Slightly skewed here, of course. We have many copies. But we're only interested in one copy, right? The rest is just copies of the original. So this would be 0, 1.
but it is only 10 and right?
This one, yes. Very good. Yeah. So this is Rx. Okay. So this is just a setup. So our X, it's some honest subset of R to the 2G. It's definable. in Rn. And now what are the torsion points? So the torsion points downstairs are tricky, but upstairs they become simple. So if P is downstairs in the Abelian variety of order, if P is 0 and T is some natural number, then upstairs in the cover, P will be the image of some rational points intersect and in the unit approximate. So this just means it's multiplication by t, 0. That means, and upstairs I'm rational because in order to divide t here, the denominator also has to be divided upstairs. So this is the connection between the torsion in the Abelian variety and the rational points upstairs. Here the degree, these will be algebraic points, but the degree will be very large. There'll be complicated algebraic points, but down in the universal cover, we'll just have rational points. It kind of reduces them to 1. Yes, yeah. Sorry, I'm using right. Okay, so that what was the upshot of everything is that 0, 1, the 2g cap due to the 2g. This is a bijection on modulo this uniformizing map with the torsion points on this. So we can really realize torsion points downstairs with rational points upstairs, but on a definable set. No longer something that's algebraic, but possibly analytic and hopefully analytic, because that's what the Pila-Wilke theorem requires. We have to remove something in the theorem to get an estimate, and that's going to cost some work later down the road. Okay. But a single rational point is not enough, right? Pila-Wilke theorem says that the number of rational points at bounded height on the transcendental part of the dividable set grows sub-polynomial. But a single torsion point will give you a single rational point. And so the upper bound is t3 epsilon, the lower bound is 1. That's not going to help. So we need some further input. And this is what has been done in the paper of Pila-Wilke. Namely, we really need that everything at this point is defined over a number field. We need the action of the Galois group. It comes from arithmetic. So here. Okay. So if my point satisfies t to the p equals 0, and everything is defined over the number field k, p is a morphism of multiplied by t is a morphism of a into itself. It's defined by some, or you can arrange that it's defined by some homogeneous polynomials whose coefficients are in k, because everything is in projective space. So this is algebraic, and the coefficients will be in k. So if I apply an element in the Galois group to the coordinates, the absolute Galois group of k, I'll get 0 again. So this is usually given by. And here we're just applying sigma to the choice of projected coordinates of P. There's other ways to present this, but this is one way to see it. So that means, of course, that the order of sigma P also divides T, and in fact, ensure that the order has to be exactly the same. Sigma. The order varies. So it maps torsion points to torsion points on the value variety. It's highly non-continuous map. It's not defined everywhere. It's defined on the algebraic points, but it maps torsion to torsion. Now we also have not only A, but with X, our subvariety that we want to kind of count the torsion points on. X is the zero set in projective space for polynomials. Okay. X naught, Xn. And so the same thing once I apply sigma to P, I also do X. So apply the Galois operation. The intersection of the torsion with X and Y. So the upshot. And this is probably the fundamental observation in the paper is that we can put the Galois group act is torsion on X. And this Galois orbit will also be in the intersection. I think it was pointed out before. So from this, it follows that P has. There's a comment before that P has is an algebraic point because the kernel of multiplication by P is strong. So this whole Galois orbit here contains only points of the same order. Have order, same one as the order. So from a single point of finite order, you get many more, or you get any more. We'll see if we get any more. That gives you more points. So the question is, how many more points do we get? More limits. A large so the silly answer, the size of this is the degree of field generated by P over K, but that's not a helpful answer. We can certainly say that, well, if my point has order T, then it'll be in the kernel of multiplication by T. And we already saw that all Galois conjugates of the point will be in this kernel. So this is bounded from above by the order of the kernel of multiplication by T. And this happens to be T to the 2G. Remember that, well, as a topological group, the value variety looks like this, and from this you can see that the number of points of order dividing T is exactly T to the 2G, and the group itself is isomorphic to this group here. So it's the kernel. So we get an upper bound, but we want actually a lower bound, we want many points. And that's what we're going to look at tomorrow, namely lower bounds. for this Galois orbit. Like there's polynomial. So the point is a lower bound, we want something from below because we want many rational points. All these points here will be those rational points upstairs. We want some growth here. This is kind of the limit of the growth we can expect to the 2G. We want some fixed power on the left hand side. So that's what we're going to see tomorrow. There's different ways to approach this. For example, if you're Serre, or results from transcendence theory.
How are you
Like
going to
us.
use that?
Excuse me?
How are you going to use it?
Oh, that's I'm going to spoil my talk for tomorrow, but I can explain it to you now. So, so we have these rational points here, and they come from torsion points in downstairs in the belly body. But the Galois action gives us some given torsion point will give us many torsion points. This is going to be what we're going to see tomorrow. That this orbit is actually quite large. It grows like some power of t, some fixed power of t. And then you get a fixed power of many rational points of bounded height on this set here. And then we can apply pure locus. Then we have to study the algebraic and the transcendental locus effects. Be able to say anything beyond that. This is what we'll cover tomorrow in the talk.
Okay.
Any questions for Philip?
There will be uniformizing mass.
Not in this proof. We just need that the uniformizing map has this property that it's analytic somehow on the box 0, 1 for 2G. If you want to go, the families of valid rides and the main these properties of these theta functions. One way or the other. Or they vary.
We already said in the beginning, but what is the aim at the end? Just to show the different reflection is finite?
Well, the aim is to, so we have the theorem that this is the theorem. X cap A towards this risky dense if and only if X is a torsion coset. So this was the translated with the balance upright by the point of finite order. And so the one direction is somehow something I sketched at the beginning. And in this direction here, this is somehow in the theory, and what we're going to show is this direction. This is going to be tomorrow. So that if I have a lot of torsion points, then X has to have a very particular
Contains.
and then X is a torsion coset. So yes, so this is what this is what I already said it actually, but so the goal is to show this like less size, right? But so it's
Any other quick questions? Before we take a short break? Okay, thank you, sir.